All right, so here we are back with part two. We're going to put it all together, right, and actually see this, breaking up all of the different pieces. Okay, so we'll say putting this all together, that'll be our, all right, so basically you have your conditions, right, hypothesis, conditions. Um, you want to, so your whole outline, right, you basically have HO P equals some P sub zero. HA is going to come from, something else, and then I'm actually going to show you that there's three possibilities. So either P is less than PO, P is greater than P sub O, or P doesn't equal P sub O. Okay, and then with your test statistic is still going to be the same. So I'm still going to write that down here, kind of like all three of these all feed into the same test statistic, right? All over, this was P0, 1 minus P0, all over N. And these distributions, right? So this is how you're going to find your p-value. So I'm kind of writing this backwards, but um, what you're doing is you're looking for the area. Okay, the way this works, if the HA is a less than, then you're finding the area in the left tail. All right, so that's your p-value will be everything to the left. If it's a greater than, you would find everything on the right side, and then that would be your p-value. If it's a not equals to, that one's actually a little bit, there's an extra step, I guess you could say, is, when you're getting a value that large or more, even though you're only going to end up on, say, one side, it doesn't matter what side, you actually have to account for the same area on the other. Okay, so the p-value would be this one and this one together. So that would be your p-value, right? So basically, you would have to find one of the tails and then double it to get the area of both, because it's going to be the same area in both. Okay, so and then you're going to use that to compare it to alpha, do your conclusion, and so on and so on. Okay, so the first example I have for you, I've got two of them for you, and then that's it. So the first one, right, would be we have a potato chip manufacturer, and with that, produce determine more than 8% of the potatoes. That's an 8%. If they have, excuse me, more than 8% potatoes in the shipment have blemishes or they're no good, truck gets sent away and they get another load. So they randomly sample 500, so to carry out a significance test at the 0.1 level. What should they conclude? Okay, so when I'm told carry out a significance test, I'm thinking phantoms right away, all blown out, every single step. You're not skipping them, full blown significance test. So the parameter, right? We're going to name that P, right? Because it's a proportion. And that would be the proportion of all potatoes in the truckload with blemishes, right? Because we're not looking at every potato, we're just taking that sample, right? But P is the proportion, and this P is not saying the same thing as the P in phantoms. This P is like the proportion that I'm talking about. Then we have HO, and we have our HA, right? So HO proportion would be 8%, right? Because that's what we would keep. We're trying to show more than 8%, so we want to show P is greater than 8%. So this is a one-sided to the right test, so a right-sided test. Conditions, right? So P is done, right? H is done. Assumptions or conditions. It says you have a random sample of 500, right? So that's good. Random sample of 500. So there's the first check. Second one, I have to assume, right, if this is a large truckload of potatoes, we're assuming that there's more than 5,000 potatoes in the truckload. Right, so in truckload. Okay, there's check. And then the third would be the NP and NQ, so there'd be 500 times 0.08 and 500 times 0.92. Those numbers would come out to 500 times 0.92. You got 40, which is greater than 10, and you have 460, which is greater than 10. All right, so that checks out as well. All right, so there's A is done. The name, we're going to run a 1 proportion z-test. Right, proportions are always z, right? So there's n. Test statistic, z equals p hat, right, which is 47 out of 500. So my p hat is 47 out of 500, right, which is going to give me 0.094. Okay, so we're going to take 0.094 minus 0.08. All right, now obviously we have some evidence because 0.094 is bigger than 0.08, but is that enough? And then you have 0.08, 0.92, all over 500. Okay, so that is going to be carried out to 0.094 minus 0.08, and divide that by 0.08 times 0.92, 500, and you've got 1.15 is your z. Okay, and then for the p-value, we are looking for a greater than, right? And I always like to write this in terms of p was the z, so I know this is a 1 minus or not. So 1 minus, second vars, normal CDF, 1.15, and this would be 0.8749. 1 minus that, and we have 0.1251 as a p-value. So we would say that 0.1251 is greater than, and that's our t, and then our O, right, obtaining a p-value. 0.1251 is greater than 0.10. So that means that we fail to reject HO. And that means that there's your M is done. So your conclusion, we would say that there is not convincing evidence or convincing evidence or significant evidence that the proportion of all potatoes with blemishes is over 8%. So what should the producer conclude? We would say that the producer should keep the truckload. All right. And with that, basically, if we were to do that, we can think like, okay, well, this could be if we made a mistake, this would be a fail to reject. So if you fail to reject, that means this would have been a type 2 error. If we made one, we're assuming we didn't make one, but if we made one, that would have been a type 2. But there's that example. I'm going to come back with one more part that's one example, and that's it, but it's very important because it's a two-sided one. So stay tuned.